Good afternoon, ladies and gentlemen. First of all, thank you for staying. I know everyone's keen to get to the conference dinner. So, my name is Gary and I'm here on behalf of SST Sensing, who are a manufacturer and distributor of liquid and gas sensors for various applications, who are a Scottish-based company, as you may gather from the accent. So today we are presenting today a new ppm or trace oxygen gaseous sensor. So I'm a physical chemist. That's my background. So this project is quite unique in that we have a three-way partnership between academia and industry. So I am the associate, and we work with academics who have years of experience in the field of fluorescence and various spectroscopic techniques, and engineers at SST who again have years of experience from product development. So here's the proposed ppm sensor which I have in my hand. This is not the size. This is for demonstration purposes. In fact, this is the size. So SST actually have an oxygen sensor on the market. So this sensor goes from 0 to 25% oxygen. So basically, the principle is the same, but what we have done is we have changed out a few of the materials or the components within the sensor and the oxygen sensing layer itself, which is what I focus primarily on. So here you can see a breakdown of the sensor. So basically, I don't have time today to explain in detail what luminescence is, but I will give you a brief insight. So basically, we have a green LED here that just pulses at a particular rate. We have a dichroic mirror here with a material that's particularly sensitive to oxygen. The dichroic mirror reflects the UV rays from the LED, and the only signals that we collect passes through the dichroic to the PCB here with the photodiode. So one important aspect when developing a commercial sensor is you can argue that virtually all sensors are sensitive to temperature. So here we have a temperature sensor on the PCB, or here, sorry, and we have a pressure sensor here as well. And I'll explain the reasons for that. So this sensor, the most widely used ppm sensor on the market is by far electrochemical. There is electrochemical or zirconia and paramagnetic sensors. Here, just like electrochemical, this sensor operates at a very low power. So at 5 volts, this gives out less than 7 milliamps. It also has a non-depleting principle, and I'll explain what that means. For example, if ppm sensors based on electrochemical sensors are exposed to ambient conditions, like what we're in now, they start to deplete. The oxygen uses up the electrolytes. So you either have to basically change out the sensor itself or have frequent recalibration. This is something that we are trying to get round. As I mentioned, we have temperature and pressure sensors to compensate for those variables, which is particularly important. ROS compliant, so that means the removal of hazardous substances. So there's no lead or any other hazardous materials in there. And that's quite crucial for certain European countries that require those aspects. Miniaturized device, as you can see, it's about 30 millimeters by 20 millimeters, so it's quite compact and it's low in cost. So what's the principle? So here's the, as you've seen, So this is the part that I've been focusing on. So we have a porphyrin complex that's extremely sensitive to changes with oxygen, but insensitive to other gases. So the way the process works is we immobilize the dye within a glass material, which is then coated with a fluoropolymer that we use. And this is all immobilized within a silicon support. So what we do is we also add in some quartz material for two reasons. Number one is that it enhances the luminescence signal. It causes light scattering. So it bounces the light signal around in the material. And number two, it offers mechanical stability. So the silicon support itself is extremely gas permeable to oxygen, but it's hydrophobic in nature, so it blocks out various other materials. So in an oxygen-free environment, in this case I've just used nitrogen as an example, the LED will pulse and hit the oxygen sensing layer, and we will get a luminescence signal that will pass to the photodiode. So here, this is the LED on time, and this is the rise from the luminescence, and we collect what we call the decay time. You can measure either luminescence intensity or luminescence decay time. We chose luminescence decay time for various reasons. Number one being that intensity-based sensors are so sensitive to changes in, for example, the output power of an LED. If that changes, the intensity will change. And in the most standard way is that you will get intensity changes from the formulation here. When you do decay time, you take out these aspects. So basically we monitor the decay every second. However, in an oxygen environment, what happens is you get a process known as luminescence quenching. So what happens is this similar thing here, but in this case, luminescence quenching causes the oxygen interacts with the luminescent dye, and the decay time becomes faster. So basically what we can do is characterize the amount of oxygen in the environment with the known decay time. So as I mentioned, you can either monitor luminescence intensity or decay time. What you can do is you can tau naught as the decay time in the absence of oxygen divided by the tau value and your known oxygen concentration. And what this does, it's known as a Stern-Volmer plot, and this gives you a linear response with oxygen concentration. So here's the process of luminescence quenching, where the little molecule collides with the oxygen and you get the quenching process. At higher temperatures, as you can imagine, everything happens much faster. So the quenching process again is much faster, and you will get an increase in the Stern-Volmer relationship. Another important factor is the response time, as you can imagine. Again, this is another disadvantage of intensity-based sensors. Here you can see that if you were to do an intensity-based sensor, the response time is particularly fast, but the recovery time is actually quite slow, about 320 seconds. The key thing here is that when you expose this ppm sensor to air, you get a nice repeatable and reversible signal. However, when we do decay time, you get a much faster recovery. So 23 seconds, and again it's nice and repeatable. This is what we call the true response time, and this is what we spec for a sensor. So here is the raw waveforms that you probably recognised earlier. So we start the ADC counts at the same rate. So we can do this by controlling the output of the LED. So for example, at 10,000 ppm, the LED has to work a little harder to get this waveform all to start at the same place. But you can clearly see that as you increase the oxygen, the decay time gets faster and faster. And you can see this more clearly in the next image there. So we've just went up to 10,000 ppm in this case, which is 1% oxygen. but we will be looking to develop this sensor from 0 to 1000 ppm. So here, if you plot the raw decay versus PPO2, you get an exponential kind of curve. But if you do the Stern-Volmer, you will get a nice linear correlation. I mentioned temperature, so we are looking to characterize and develop this sensor from -30 Celsius to 60 Celsius. Again, you can clearly see that as you increase the oxygen and the temperature, the decay time will continuously drop. Again, if you plot the Stern-Volmer, you get a nice linear correlation. You can see that the sensitivity at 60 Celsius changes slightly, but we can characterize that from the decay time here. This is just a difference in the solubility of the oxygen passing through into the materials at that temperature. This makes calibration so much easier that we have a nice linear correlation over the full range from -30 Celsius to 60 Celsius and 0 to 10,000 ppm. What this shows, so this is what we call a verification. So we get all the values at 20 degrees Celsius over the full range. In this case, we're going to 1000 ppm because that's what we're trying to do. So the blue here is the applied oxygen concentration that we see from our gas blending system. Then we put the sensors through the calibration process, so going from -30 to 60 Celsius, from 0 to 1000 ppm. Then what we do is we record the sensor output in ppm from what we've seen from the calibration. So we compare the data before calibration to what we compared after. And in this, so what this did was give us a nice error of plus or minus 15 ppm in this case. So this is the absolute error of the sensor over the full calibration range. So here's just a few of the specifications from the sensor that we are happy to say to date. So I mentioned low power, so at 5 volts, less than 7 milliamps. The response time of the sensor, as you've seen, is less than 30 seconds typically. You have slight variations from sensor to sensor. The operating temperature, again, this is one thing that's really crucial because most ppm sensors, again, such as electrochemical, go from around about -10 or -20 to about 50 to 55 Celsius. So we're trying to make an improvement on that. We have the pressure sensor in there, so what we can do is we can actually monitor the partial pressure of oxygen. And again, this takes any pressure variations out of the equation. And this gives us a more accurate representation of the reading at ppm. So for example, if the pressure today was 1200 millibar and the PPO2 was 1200 microbar, then the ppm is 1000. So for the work, we are just looking at doing some final software revision to actually give us the TOR value to correlate with an actual O2 reading. Looking at calibrating the sensors, multiple sensors. So we're looking to calibrate around 400 sensors simultaneously. We're looking at integrating a humidity sensor. The formulation is virtually identical to what we have just now. So we know that from 0 to 99% relative humidity, as long as it's non-condensing, there's no effect on the sensor itself. But we're looking to add a humidity sensor as customers have been looking for that. Drift characteristics, virtually all sensors have some degree of drift. We are looking to monitor if this is the case for this sensor. And the operational lifetime of the sensor, so that's basically the photo degradation and the photo bleaching of the sensor. Again, similar formulation to SST's current sensor. which is a specification of 5 years or greater than 5 years. We're hoping that this is also the case, and we're hoping to launch the product Q2 of next year. At this stage, I'd just like to thank the rest of the KTP team who are all here in Orlando, apart from Mahesh. If you've not already been, Craig and Paddy are demonstrating or exhibiting next door at booth 19. So if you've not had a chance to see the sensors in operation, please come along tomorrow. And I'd like to thank the rest of the SST team, all the engineers out there. Thank you.